Hello everyone, welcome to the 16th lecture for the NPTEL course on computer system optimization for machine learning. As usual, we will first give you a brief recap and then we will continue on iris. Okay. So, in the last lecture we started discussing about row stationary data flow, where each primitives operate on one row of filter weights and one row of input feature map to produce one row of partial sums, and then the partial sums are accumulated to generate the output feature map output feature map value. And then we discussed about the example with 1D convolution, right. Now, if we look closely in this row stationary data flow, how many partial sums need to be stored? That is the same as the filter row size, right. So, we have to store this value, this value and this value. So, since we have in this particular case the filter row size is S, we need to store S number of partial sums. And where should we store? We need to store in the scratch pad which is there inside in each of the processing element, right. Now, the total partial sum capacity, the total scratch pad capacity, or the scratch pad should store the weights. We have S number of weights, which is nothing but the filter row. If we have S number of weights, we have to store the S number of input feature map, right. So, remember we are performing the element wise multiplication with respect with each of the weights with each of the input feature map. And finally, we have to store one partial sum per input, correct. So, that is why the total scratch pad capacity has to be S plus 1, which is nothing but 2S, right. So, that is the scratch pad capacity. Now, let us see how this row stationary data flow work in case of 2D convolution, right. So, for 2D convolution we have, let us say this PE array, or this is the 3 by 3 PE, and if we have 3 by 3 PE, that means we are actually performing a convolution where we have this 3 by 3 filter which is getting convolved, and then let us say we have total 5 rows. That means let us assume that the image size is 5 by 5. Okay. So, this is the 5 by 5 input feature map, or 5 by 5 input images, and then this is the 3 by 3 weight, right. So, ideally the convolution will happen first, this 3 by 3 will be projected on this 3 by 3 patch, right, and then all there will be element wise multiplication with the filter values with this input feature map, and then all the values will be added to get the first pixel, right. Now, remember here we are trying to do row stationary data flow. That means we will first, so if we do this convolution, then we will get, let us assume the stride length is 1, then we will obtain output feature map of size 3 by 3, correct. So, in row stationary data flow, the idea is to generate this is the output, by the way. So, this is the 3 by 3 output. In row stationary data flow, the idea is to generate this one row of output feature map in one go. How is it done? Let us see. So, to do that, we have to slide this 3 by 3 kernel onto this 5 by 5 input image for the full row, right. So, that is why this row 1 of this filter, again green means the filter weight, blue means this input image, light pink means the partial sums. Okay. So, the first row of this filter is convolved, or we are performing the element wise multiplication of this first row of the filter with this first PE, right. So, similarly the second row of this filter will be element wise multiplied with the second row of the input image, and then the third row of the filter will get element wise multiplied with the third row of the image, right. Now, each of the PE is actually responsible to perform this element wise multiplication for each of the row of the input image, right. Now, so first PE will perform this portion of the filter multiplied by this portion of the input image, that will happen in the first PE. In the second PE, it is performing the row wise. So, it will happen, it will perform the element wise multiplication with this portion of the filter with this portion of the input feature map, and the third PE will perform the element wise multiplication with the third row, correct. And then they will all get added up to get the one particular pixel, right. So, they will get added up to compute to have the partial sums of one particular pixel, like this pixel, correct. Now, again the same thing will happen, the same rows has already been provided to these P's, right. So, in the next iteration or the next time, the same operation will happen on this particular chunk of the input feature map, right. I am just highlighting this particular chunk of the input feature map, that will generate this particular pixel of the output feature map, and in the next round this particular chunk of the input feature map will get convolved to get this particular pixel in the output feature map. Now, everything is happening in this particular set of P. Okay. So, this set of P has the information of row 1, row 2, row 3 of the input feature map. They will get convolved, or they will get element wise multiplication, element wise multiplied with the row 1, row 2, row 3 of the filter weights to obtain the first row of the input image, right. I hope it is understandable. Now, similarly, to get the second row of the input image, now we have to feed row 2, row 3 and row 4 of the input image, right. So, this row 2, row 3 and row 4, this has to be fed to the P, same weight values has to be fed to obtain the second row of the output feature map, right. Now, similarly, row 3, row 4 and row 5 has to be fed on this set of P to obtain the row 3 of the output feature map. So, that is how this row stationary data flow work. So, from each set of P we are obtaining one particular row of the output feature map. So, that is how this row stationary data flow work. I hope you understood it. Now, again we just saw the row stationary data flow as an extension of the 2D convolution, which consists of several 1D convolution. Now, in Iris architecture, they have incorporated a P array of size 14 by 12, which is performing this row stationary data flow based convolution. Okay. So, this particular this 3 figure is showing the data flow of filter row, then input feature map row as well as the P sum row. We all just saw that filter rows are exactly the same, or filter rows are provided into all set of P's in exactly same way. The input feature map rows are provided in diagonal fashion, right. I will just go back. So, you can if you remember, this set of P are getting row 1, row 2, row 3 of the input feature map. This set of P are getting row 2, row 3 and row 4 of input feature map, and then this set of P is getting row 3, row 4 and row 5 of the input feature map, right. So, that means the input feature map is actually flowing diagonally, right. Now, with that, the partial sums are flowing upwards. So, whenever we are computing this partial sums from each of these P's which are in this vertical direction, we are getting one row of the output, or the partial sum corresponding to one row of the output, right. So, that is how this row stationary data flow work in Iris, correct. Now, if you remember, when we were discussing the high level architecture of Iris, we saw that they have proposed something called RLC, or run level encoding, right, run level coding in short. Now, remember, there are, like I was saying, like there are two much of the data communication between the PE array, global buffer as well as the other scratchpad memory etc. right. Now, whenever we have data communication, it takes some time, nothing is free in the computer, like whenever the data is going from one part of the computer to the other part of the computer, it takes some time, energy etc. right. So, our goal is to how should we minimize the data flow. So, remember whenever we are saying communication involves just flowing of some bits, some numbers, right. All the numbers are obtained from the convolution or some input output activation or some weights, some data is getting flown from one part of the accelerator chip to the other part of the accelerator chip. Now, it has been seen, I mean if you implement one convolutional neural network yourself, you will see that lot of those activation values are actually zeros. So, there are lot of zeros in the data whichever is communicated from one part of the accelerator to the other part, maybe it is between two layers or something like that, right. So, this is one example of the input, like we have 0 0 then 12 then 0 0 0 0 53 and then 2 zeros and then 22. Now, when there are lot of zeros in the communication data, then it leaves some room for improvement, right. So, run level coding is one such way to optimize the communication. So, if we do not optimize, let us say all the data is encoded or all the data is represented as 32 bit floating point number, then we have to actually communicate 32 bit for everything. So, remember even if we put 0, it is a 32 bit 0. Okay. If we do not optimize anything, we have to, like there are wires, parallel wires which will carry the value of 0, correct. So, we have to carry 32 bit 0, nothing is free in the hardware if you do not optimize. But with run level coding, what we can do, we can compress the communication. So, we can say that we have a run of 2 zeros and then the level is 12. So, there are 2 zeros. So, we can say that there are run of 2 zeros and then after 2 zeros the level is 12. Similarly, we have here run of 4 zeros and then level of 53, after that run of 2 zeros and then level of 22 and then this is the terminal bit. So, now in iris architecture they have put 5 bit for run and 16 bit for level, right. So, you can see that there is a slot of 21 bit where 5 bit is for run and 16 bit is for level, and then again we have 5 bit, 16 bit, 5 bit, 16 bit and then finally 1 bit. So, this is a chunk of 21 bit, this is another chunk of 21 bit, this is another chunk of 21 bit and finally 1 bit. So, this is in total there are 64 bits, right. But so, I just told you that 32 bit, but they are not representing the values in 32 bit, they are representing in 16 bit. So, if we have 16 bit representation, then in 64 bit we can only have 4 values, right. But here with this run level coding, we actually have 1 2 3 4 5 6 7 8 9 10 11 values, correct. So, we can pack 11 values in 64 bit with this optimization, right. Now, you can say that what if 5 bit means we can put the maximum number we can put is 31, right. You can say that what if there are more than 31 zeros, then we will put 31 here and then level of 0. So, if we have like let us say 54 zeros, then for the run we will put 31 and then we will put 1 0, still 54 minus 31 which is like 23 zeros are remaining. So, then again there will be run of 23 and then the level will be whatever is the value after 54, let us say the value is 16, then we will have 16 here. So, that is how this run level coding works. Okay. So, I hope you understand, and now if you see the architecture, in the architecture they have this run level decoder as well as run level RLC encoder and RLC decoder, right. So, whenever the data is going from the global buffer towards the off chip memory, then they are compressing the data through this RLC coding, right. So, whenever we are compressing, that means the less amount of data is accessed to or fro DRAM, and that is the if you remember, I am telling you again and again, whenever we have a memory access to or from DRAM, that is a killer, right, that will take lot of latency, lot of energy. Now, since we have this run level coding, we are actually compressing the data and then sending to DRAM. Whenever we are fetching from DRAM, we are getting that compressed data. So, in between there is RLC decoder and RLC encoder. So, the amount of data access to and from DRAM is less. So, that is how they are actually reducing the number of DRAM access. As you can see, let me erase some of the parts so that you can see the figure. You can see the uncompressed versus compressed for different AlexNet configuration layer. You see that the DRAM access required for uncompressed is always like 1.2 to 1.9 times higher for different convolutional layers. So, they are, when they are compressing with respect to this RLC coding, then they are saving a lot in terms of the DRAM access, which is a huge benefit, right. Now, as I was saying that there are multiple components in this IRIS accelerator. There is a global input network which consists of Y bus and X bus. So, there is a vertical Y bus which consists of 12 horizontal X bus. So, remember we have a 14 by 12 P array, that means there are total 12 rows, that is why we have 12 horizontal X buses. Each X bus is connected to 14 PE at each row. So, there are 14 columns, right. So, there are 14 PEs in each row. So, each of these X buses are connected to 14 PEs. Now, there is a multicast controller which decodes the destination. So, whenever a packet comes, it has to decode the destination. So, first it will go to the X bus, and then whenever it is in that X bus, it needs to know its destination. So, there is a multicast controller which decodes the destination. Then inside the processing element, they have multiple levels of optimization. So, first they have 16-bit 2-stage multiplier and adder. So, this is the 2-stage pipelined multiplier, and then they have adder also, which is 16-bit adder. But more than that, they have introduced something called data gating to reduce the energy consumption. So, remember, as I was saying that there are lot of zeros in the data, right. Now, if we have lot of zeros in the data, then it is wasteful to compute multiplication or addition with respect to 0, right. I mean, again, if we do not do optimization, still if we, let us say we are multiplying one 32-bit value with a 32-bit 0, that multiplier circuit will be active even if we are multiplying with respect to 0. That whole multiplier circuit will be active, whatever latency it will take for regular multiplier, it will take the same amount of latency even if we are multiplying with respect to a number 0, right. If we do not do any optimization, but then we can perform a data gating where we can just see whether the data is 0. Now, if it is 0, then we can directly put the data, or we can directly we can bypass some of the unit, we can bypass some of the scratch pad and all those things. So, that we can say that if the one value or one input to the multiplier is 0, the output is always 0, correct. So, that is data gating, and data gating reduces the energy consumption, which is shown in this red dashed line. Now, finally, IRIS is also a fabricated processor, it is a co-processor. So, remember, whenever we talk about processor, yes, I mean it can be a standalone processor, but whenever we say co-processor, that means it needs a host processor to be active. So, this is the picture of the IRIS co-processor, where we have this PE array with 168 P's, and then there is a global buffer of size 108 KB. Okay. So, this is a 3.5 by 3.5 chip, which is like 12.25 millimeter square, right. Now, to function this co-processor, we need a host processor. So, as you can see, they have this setup, they have a Xilinx FPGA, and then they have this Jetson NVIDIA Jetson processor, and then finally they have the IRIS chip. So, this Xilinx FPGA interfaces between the NVIDIA Jetson device and then the IRIS chip. So, the NVIDIA Jetson offloads some of the tasks, some of the convolution operation tasks to Iris, Iris performs the task and then sends back to Jetson. That is how the Iris works. So, without a host processor, Iris will never work. So, that is why Iris is a co-processor. Now, let us see some of the results of Iris. So, first of all, let us see the area breakdown. So, this particular pie chart is showing the area breakdown of Iris core, where you can see that the PE array takes 78.6% of the area, this blue region, and then the next highest consumer of the area is global buffer, which is 18.8%. So, NOC takes 1.8%, then run length codec and ReLU takes 0.3% and so on and so forth, right. So, most of the area is consumed by PE. Now, if you concentrate on each of the PE, so you will see that 61% of the PE is taken by scratchpad, multiplier and adder is taking 9.4%, control is taking 11.4%, and then FIFO is taking 18.3%. Now, in total, again remember, we can say that all these DNN algorithms are compute intensive. So, we need more area for compute, but no. So, here from here you can say that the PE is taking 80% of the area, but inside PE 60% is taken by scratchpad and 18% is taken by FIFO, right. So, I mean 80% is PE, but then out of 80% you have 61% is taken by scratchpad and then 18% is taken by the FIFO, right. So, that is another 80%, correct. So, 80% of 80% is 64%. So, 64% of the total area is taken by the buffers or the memory inside P, and then we have anyway 20% for the total for the global buffer. So, total 84% of the Iris chip is taken by memory. It can be global buffer, it can be scratchpad, it can be FIFO. Only 10% of these 80%, which is like 8%, is taken by the compute, the multiply and adder. So, again the bottom line is we may think that compute is the key, compute will take higher area of any of these accelerator or any of these ML algorithm accelerator, but that is not the case. It is always the memory, it is always the storage, right. So, similarly, let us see what happens in terms of power when we execute AlexNet. So, this is the pie chart for convolution, and this is the convolution 1, the first convolution layer, and this is the pie chart for the fifth convolutional layer. Okay. Now, again in this case also you can see that the 42.5% is taken by scratchpad. Clock. So, whenever we have multi-core processor, then clock routing is another area which takes, or another thing, another component which takes lot of area, lot of power. In this case also you can see that the clock network takes 33%. Multiplier and adder, the core compute unit takes only 8.9%, only 9%, right. For convolutional for fifth convolutional layer also you can see that 33% is taken by scratchpad, 45% is taken by clock. Multiplier and adder takes only 3%, very small portion is going on to computation. Most of the power is going onto the buffer operation, the clock network, some control, FIFO, etc. So, only 2% is gone into computation, right. So, that means yes, we need computation, but then at the end of the day most of the power, most of the area is actually consumed by some other part which is required to aid the computation, buffers, clock, then control, right. So, that is a big takeaway for all of you, like whenever we think about these ML algorithms, we may think that okay, ML algorithms are too compute intensive. So, we need to make better multiplier, better adder, but no, at the end of the day we can see that we need to make better storage, better memory, right. And that is why there is a global shortage of RAM. Why? Because people are now realizing that we need more memory to sustain the training as well as the inference of all these ML accelerators. Okay. So, that is all for this lecture. I think we got enough idea of how these DNN accelerators will work, and what is the main consumer of power, area, etc. So, in the next lecture we will see a better version of iris, which is iris V2. Till then, thank you very much. See you next time. Bye.